Let's talk about writing reaction mechanisms for writing a reaction mechanism for an alkene when you add hydrogen halide, right? Now, as a student, you can be asked to write a reaction mechanism, or you might be asked to interpret curved arrows. If you're just asked to write the product, then the video that just shows the reaction for the addition of HX to an alkene will give you that. But I promise you, if you know how to write a reaction mechanism, it makes you being able to write any product pretty simple because you understand what's going on in the reaction. So let's write the reaction mechanism, and I'm going to use 2-methyl 2-butene as the alkene, and I'm going to add HBr to it. This reaction has two steps, right? In step one, and step number one is separate from step two. Let me start out with that. Please don't do step one and step two together. You, this first step can either be called a proton transfer, or it can be a nucleophile making a new bond with an electrophile, or it can also be called a nucleophilic attack. Whichever one you choose is fine. Just make sure you know what's going on here. All right. So remember, and if you have not watched the video on arrow pushing or the four mechanistic properties that happen in any organic reaction, please go back and watch it because it will help you understand the curved arrows better. So we have an alkene and we're adding HBr to it. If you've watched the video that just shows how to get the product, you should know the first thing we have to do here, you have to break the carbon-carbon double bond before any of these can be added to it, right? In a reaction, you need to always identify your source. This is your source, and your source is rich in electron. The source in this reaction is a carbon-carbon double bond, right? Your sink is your hydrogen, right? It's a rich poor thing we're doing here. Rich in electron is looking for something poor that it can give some electron to. All right, so let's draw our arrow showing our proton transfer, right? Our nucleophile making a new bond with our electrophile. So in this reaction, your source is your nucleophile, right? And the hydrogen over here is the electrophile. So electrophile, nucleophile making a new bond with an electrophile. Let's draw our curved arrow. So let me bring this down just a little bit. Let's draw a curved arrow. You draw your arrow, the tail of your arrow will start from your source and the head will end at your sink, right? Now remember, where the head of the arrow ends, either you're making a bond or a lone pair, or you're forming a lone pair. Here we're forming a bond between the hydrogen and one of these carbons, either carbon 2 or carbon number 3. So this arrow, our first arrow here, is indicating the double bond breaks to make a single bond. So your carbon-carbon double bond breaks to make a carbon-carbon single bond. That's what that arrow is indicating. And it also is indicating that the hydrogen is going to bond. And in this case, your hydrogen is going to bond to carbon number 3 based on Markovnikov rule, right? Carbon 3 has one hydrogen. Carbon 2 has no hydrogen. Markovnikov rule states that your hydrogen will add to the carbon of the carbon-carbon double bond with the most hydrogen, okay? So your hydrogen will bond to carbon 3. So that's what this arrow here is telling me. Double bond is breaking, right, to become a single bond, and my blue hydrogen is adding to carbon number 3. Now, let's remember something here. If hydrogen is going to go with carbon 3, I need to show hydrogen breaking up with bromine. Remember how we break up? We steal the electrons. So these electrons are right now being shared between hydrogen and bromine. But for the breakup to happen, bromine has to take all the electrons to itself, right? Or look at it another way. Hydrogen can't have two bonds. So when hydrogen makes a bond with this carbon, right, you must break the bromine away because hydrogen can't look like this. We chemists will lose their mind if they see this, okay? Cannot have two bonds, so you must break the bond, all right? Now, remember this. When you draw curved arrows, they're specific, they have meaning. What these arrows indicate must be shown on the product side of your reaction, okay? This step in the reaction, step number one, is your slowest step. And your slowest step is the rate determining step. And I know you knew that because you were great at kinetics in Gen Chem, okay? So this is your slowest step, all right? And I'll talk to you about slowest step and activation energy in a couple seconds, all right? But let us now interpret what our curved arrows mean, okay? So always draw your carbons back. You didn't lose anything here, draw them back. So let's draw 4 carbons. Let's draw 4 carbons. Carbon 1, 2. So this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, right? On carbon number 1, I have 3 hydrogens. Please put them back. Carbon 2, I have a CH3. Please put it back. My double bond between carbon 2 and 3 is now a single bond. So please don't draw no double bond over here. We broke it, okay? So on carbon number 3, right, I have this hydrogen. Please put it back. But when we broke the double bond, my blue hydrogen is adding to carbon 3 based on Markovnikov rule, right? Okay, I'm assuming you remember Markovnikov rule. Now carbon 4, and I actually repeated it earlier, right? Put the 3 hydrogens back. So put these 3 hydrogens back, all right? Cool. Now let's talk about something before I talk about the bromine. On carbon 2, this carbon only has 3 bonds, right? A carbon with 3 bonds must have a charge. It's lacking at full octet. So there's a positive charge here. This is called a carbocation. And it's specifically a secondary carbocation, right? It is called a secondary carbocation because how you identify your carbocations, because you can either classify them, and if you go to my video on carbocation stability, it will explain, right? But you have different classifications of carbocation. They can either be primary, secondary, or they can be tertiary. How do I identify a carbocation as primary, secondary, tertiary? Find the carbocation, which is the carbon with the positive charge, then count how many carbons are directly bonded to it. Here's my carbon with the positive charge. I have 1, 2, 3 carbons directly bonded to it. I'm sorry. This is a tertiary carbocation. My apologies. So we have a tertiary carbocation. Now, your tertiary carbocation is more stable than your secondary, than your primary. So in terms of stability, your carbocation tertiary is more stable than your secondary, more stable than your primary, right? So this is the more stable carbocation, and I am going to explain why this is the carbocation that the reaction goes through. This is how I will explain Markovnikov rule. We'll do that in a second. So plus, remember what's going on with our bromine, right? So your bromine is stealing the 2 electrons. Remember, this bond means that 2 electrons are being shared between hydrogen and bromine. When you draw arrow from a bond onto an atom, it means the 2 electrons in this bond now belong to bromine. So let's draw bromine back. So here's my bromine. Bromine has these two electrons, these. So it has six electrons or three lone pairs. So here, 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 here. And then I gave bromine two more electrons. So now it has eight and a minus charge. Now, if you don't see why bromine has a minus charge, you can reason it out. Bromine has no charge when it has a single bond and three lone pairs. But I'm giving bromine two electrons. It's no longer being shared, increasing the negativity on bromine. Hence the minus charge. Now, this right here is step one of your reaction, right? Students tend to do this a lot. They write step one and step two together. You cannot. You need to, in step number two, right? You need to redraw your products from step one. So redraw your carbocation, CH3, CH3, CH3 with the carbocation, H, H that I added according to Markovnikov rule, plus bromine. Now, for this reaction, you should be able to see easily what's your nucleophile and what's your electrophile, right? Your nucleophile in this reaction, there's only one thing that could be your nucleophile or your source. It's the bromine, right? And your sink clearly is this carbocation because the carbocation has an empty p orbital and can accept two electrons. Or if that's too much chemistry for you, it has a positive charge, right? So clearly it lacks electrons. Electrons are negative. So you will draw an arrow from source to sink. So you draw arrow. Remember, your arrows are either drawn from lone pairs or bonds to the positive charge. This arrow means that bromine makes a bond. Let me number my carbons. Makes a bond with carbon number two. Okay? So, and this, by the way, is your fast step. It's fast because this is an intermediate. Your carbocation is an intermediate. You meet other intermediates as you learn organic chemistry. But intermediates are extremely reactive because they lack electrons. So they are happy and quickly ready to gain electrons. So that's why they're so reactive. So as soon as your carbocation is formed, it reacts immediately, right, with the bromine. And the product you get, and I'm going to draw, generally I would draw the product here. Let me try to move this and make some space. So let's move this and make some space over here. There you go. So let's draw our product. The usual, put back your carbons because they didn't go anywhere, right? Then the things that you didn't use up, please put them back. So we still have three hydrogens here. Carbon 1 has, carbon 2 has CH3. But remember now, the two electrons here on bromine, I'm using up these two electrons to make a bond with carbon 2. So carbon 2, we're making a bond with bromine. Remember, I use up these two lone pairs, so I only have these left, okay? Carbon 3, hydrogen, and that right there is your reaction mechanism, right? For any alkene plus HX, the concept is the same. The only thing they will change is the structure. So if you get the concept, it doesn't matter what structure you have, you should be fine. So this is your nucleophile or your source. And this right here is your electrophile. And what's acting as your electrophile is right there. Remember, most reaction is an electrophile and a nucleophile relationship. Even if you do a proton transfer, you can look at it as an electrophile, nucleophile relationship. Now, let's talk about why Markovnikov rule is actually right and why he made sense. Okay? Now, something to remember, and I'm going to move step two so we can talk about it. Something I need you to remember is that in terms of carbocation stability, right, your tertiary carbocation is more stable than your secondary, more stable than your primary, right? I need you to remember that. Now, based on what we have here, we followed Markovnikov rule, right? Markovnikov rule states that your hydrogen will add to the carbons that are between the double bond, that's carbon 2 and 3, with the most hydrogen. So carbon 3 has one hydrogen. This is a CH3. Carbon 2 has no hydrogens directly bonded to it. Carbon 3 has one hydrogen bonded to it and a CH3. Carbon 2 has a CH3 and a CH3. So this carbon has the most hydrogens because carbon 3 has one hydrogen directly bonded to it. Carbon number 2 has no hydrogen, right? So when you break the double bond between carbon 2 and 3, your hydrogen will add to carbon number 3 or the carbon that is the least substituted. I did speak about substituted carbon in the video about just the reaction of alkene with HX. You can go back there to see that if you have forgotten. Now, we follow Markovnikov rule, right? So we add the hydrogen to carbon 3 and we generate a carbocation. Now, this carbocation is tertiary. What if we disobey Markovnikov? Huh? Let's disobey Mark and see what happens to us. Let's disobey Markovnikov. So we're going to disobey Markovnikov. So let's redraw the alkene in question. And we're going to disobey Markovnikov rule. I'm going to show you why he's right. They don't just get up and give people PhDs, right? They got to make some sense with whatever they present. Here we go. So let's disobey Mark. So we are going to disobey Markovnikov rule and see what carbocation we generate. So here we go. We're going to disobey Mark. Remember, we're being disobedient. So we are going to carbon 1, carbon 2, carbon 3, carbon 4. We are going to add our hydrogen. And I know you already is like, lady, yes, we know where we're adding hydrogen, right? Because we're disobeying Mark's rule. Carbon 1, 2, 3, 4. Where did I get 5 carbons from? 1, 2, 3. I drew an extra one. All right, cool. So let's do this. Let's put back the stuff that we haven't done anything to. Carbon 2, carbon 3 has a hydrogen on it, right? Carbon 4, I'm putting back what we haven't used up, all right? So here's my double bond between carbon 2 and 3. I'm disobeying Markovnikov rule, which means I'm going to put this hydrogen on carbon number 2. Based on the fact that Markovnikov rule says the hydrogen adds to the carbon of the carbon-carbon double bond with the most hydrogens. We're doing the opposite of that. So if I do that, my positive charge is now on carbon 3. Now let's talk about what type of carbocation carbon 3 is. How do we find the carbocation? I know you're already telling me. Find the carbon with the positive charge, right? Then look to see how many carbons are directly bonded to it. 1, 2. This is a hydrogen. Directly bonded here is a hydrogen, carbon, carbon. So this is a secondary carbocation. Let's look at our stability table. Your tertiary is more stable than your secondary. So Mark was right because a reaction is going to choose to go through the more stable carbocation because that will generate the more stable product. People over here in chemistry like stability, okay? So the more stable carbocation is what the reaction will go through, not the least stable. This is why Mark is right. He's right because when you follow that man's rule, your reaction will go through the more stable carbocation and you get the more stable product. If you don't follow Mark's rule, then you're going through the more unstable product and that will not even be formed. So that's why Mark is right. Even if you don't care if Mark right? Please remember his rule because they apply to a lot of reactions in reaction with alkene, alkynes, etc. Now, let's talk a little bit. Let's look at an energy profile diagram for a minute just to see why step two is fast, why step one is so slow, right? Um, you might be asked questions about your reaction. This is an energy profile diagram, by the way. And it's the same reaction. It's just that what you're seeing here is line angle. Whoops. Yeah. Let's move this up. And it depends on what you're asked or what you need to explain. Um, but it's good to understand your energy profile diagrams. It helps you really see what really takes place in the reaction, right? So let's talk about it. So these are your starting materials, right? This is the same alkene. It's just that it's a line angle formula, but I believe in you so much because you're a pro at line and structural by now, okay? So this is your line angle. You're adding HBr to it, right? Energy is on your y-axis and reaction coordinate is on your x. So this is just showing how your energy increases, right? This represents your reactants, right? And your reactants are these two things, the alkene plus HBr, okay? Now, where you have these humps on this graph, this is your transition state, and this is transition state number one, which is for step one. This is transition state number two, which is for step two. So your humps is your transition state, right? Your energy between your transition state and your reactants, this line right here, that's your activation energy, right? So we will react your alkene with HBr, right? Remember what happens in that first step? Let's go back here. Your first step is where the double bond breaks and your hydrogen adds to carbon 3 and the bond between the hydrogen and the bromine breaks, right? Now, your transition state is exactly what the word transition means in English. In your transition state, right, there's partial bond breaking and partial bond forming. So in this particular reaction, what you would see is, and your partial bond breaking and bond forming is generally shown by dashed lines. So for this, what you will see is carbon 1, carbon 2, carbon 3, carbon 4. You will see a partial bond breaking, right, between carbon 2 and 3. That's a double bond breaking, right? And when the double bond breaks, your hydrogen is going to be adding to the carbon of the carbon-carbon double bond with the least number of hydrogens, which is carbon 3. So you will have a partial bond formation, and you can show that like this, formation between the carbon and the hydrogen, and then a partial bond breakage between the bromine and your hydrogen. That's how you will show that, right? Hydrogen is adding, and remember we're generating a carbocation over here. Slightly negative charge would be on your bromine. So remember, in transition states, your transition states will show partial bond breaking, partial bond formation. Remember, in your first step in this reaction, we're breaking the double bond, so you show that with the dot line to show that the double bond is breaking. This here is showing the formation of the bond between the carbon and the hydrogen, right? And that is carbon number 3. Let me make sure we have the right carbon, yes. Based on Markovnikov rule. And then remember, for us to steal the hydrogen bromine, we will break the bond between bromine and hydrogen. Now, Here is where you find your intermediate, right? So your intermediates generally sit in the valley, right? So your carbocation intermediate is sitting here in the valley. That's now your new reactant for step number two. These are your two reactants for step number two. Let's go back to step two. Here's my carbocation. Here's my Br. They're my new reactants. So the activation, because remember, activation energy is between the transition state and your reactants. This is step two. So your activation energy for step two is between the starting materials for step two, which are these two, and your transition state, right? Notice how small this is, which means that's why the reaction is fast. Because to start the reaction, I need a whole heap of energy, whatever this is. Let's say, I don't know, 100 kilojoules. This clearly is way less. So if I need less energy, then things are going to go quicker. The reason this is so small is because your carbocation has an empty p orbital and it will quickly gain two electrons. Or look at the fact that the carbon has three bonds, which means it doesn't have a full octet, and we love to be stable. Hello, I need my 8 electrons. So the carbon will attract two electrons quickly. That's why this is fast, and the fact that this is fast means it takes less energy. Really small energy reaction happen immediately, almost immediately when you have a carbocation. Your transition state to here, right? Remember, for this transition state, the carbocation and your bromine is making a bond. So you will show a partial bond breakage between this carbon and your bromine. So that's how you show, like, your transition states show partial bond breaking, partial bond forming, right? When you get to, for example, here, your intermediate, nothing is transitioning anymore. We're done with the transition state. We have completely lost the double bond that was breaking here. It's completely lost here. And our hydrogen, even though it's not shown, it's added, right? It's now fully added. And here, your bromine has broken away, which is why in your intermediate stage here, it's by itself. Remember, transition is the only place where you show partial bond breaking and partial bond forming. At the intermediate stage, we're not transitioning anymore. Hello, I have formed my carbocation completely, and I now have my minus on Br. And it's the same thing here. In this transition state, you will show that you show a partial bond formation, right, between the Br and the carbon. So that would be your Br and your carbon making a bond, right? Partial bond formation. But look at the end of the reaction. You completely now have your product, right? There's no transition state here. I have completely made the bond between the bromine and the carbon. So something to remember in energy profile diagrams. Your transition states are generally at the highest point on the graph, right? These humps are generally a transition state. Your dips, which we call valleys, are where your intermediates are. Now, if you're ever asked to write the reaction mechanism for the reaction of an alkene with hydrohalogenation, which is a hydrogen and a alkyl and a halide, you will be fine. Here's how. Get the concept. Get where things are adding and the rule that it follows. Because even if you get a different structure, it doesn't matter. Your focus is right at the two carbons of the double bond, and you just need to follow Mark rule, right? Now, and find the electrophile nucleophile. Um, Sometimes questions might ask you to identify different things on energy profile diagram. You also should be able to do that no matter the alkene. Remember, organic is a pattern, right? And like I said, it's memorization, but you also must, the things you memorize, if you don't know how to use them, you're going to be in problems because the structures will never be the same. They give you different structures. Get concept, memorize, okay? It's the difference between organic and, let's say, biology. You memorize stuff in biology and put it back on paper. In chemistry, whatever we ask you to memorize, we're not gonna nobody's gonna ask you, oh, what's Markovnikov rule, right? fine. If even if you get asked that one time, that's 1 point, okay? But then you have to be able to use Markovnikov rule and apply it to structure. So remember, organic is a lot of concept. Memorize some things, but we're not gonna ask you to put that back on paper. You need to be able to use what you memorize.